Continuing with the section 2.7 notes, we're on example 3, part C, and we're trying to draw just a rough sketch of a graph using transformation rules. And for part C, we have a different function. The parent function here, notice the square. So the parent function is the squaring function, and you may recall that's a parabola with vertex at the origin. Our equation could therefore be written as y equals f of x minus 1 plus 2. So there are actually two transformations being applied to our parabola. The plus 2 is going to shift the parabola 2 units up. The minus 1, which occurs inside the function, being subtracted from x and not from f of x, will shift the graph to the right 1 unit. So what's going to happen to, say, the point originally at the origin, the vertex, it will be shifted 1 unit to the right and 2 units up. And now will be located at the point 1, 2. And then you'll have that parabola that we saw in the previous section, the squaring function. Looks exactly the same, but shifted 2 units up and 1 unit to the right. So you can have multiple transformations applied within the same equation. Another type of non-rigid transformation is a reflection. Given a function f, the graph of y equals minus f of x is the graph of f reflected about the x-axis. That is, you take the graph of f and flip it over the x-axis. That gives you the graph of minus f. Another reflection is f of minus x, where the minus sign is applied to x rather than to f of x. In this case, the graph is reflected about the y-axis. So the shape is going to be the same, but the graph may appear to have a different orientation. It may be opening down rather than opening up, or something along those lines. Let's look at an example with the square root function again. The graph of f of x equals square root of x is shown below, graph the given function. So minus square root of x, this would be y equals minus f of x. So this would be the first type of reflection, a reflection about the x-axis. So basically every point gets reflected across the x-axis. The point at the origin will not move, but the point at 1, 1 will move to 1, negative 1. The point at 4, 2 will move to 4, negative 2. All the other points following suit. And what we get is a graph that looks like the original, but is sort of upside down. Like so. So that's an x-axis reflection. And notice where the minus sign is in part B. It's on the inside. This is y equals f of minus x. So this would be a y-axis reflection. So here every point gets reflected across the y-axis. For example, 1, 1 is now at negative 1, 1. 4, 2 is now at negative 4, 2. So again, the shape is the same, but the orientation has been reversed so that now the graph opens to the left rather than to the right. I would also point out for the equation in part B, if we consider the domain, we would want minus x to be greater than or equal to 0 so that the number under the square root is non-negative. If we divide both sides of this inequality by -1 to solve for x, it flips the direction of the inequality symbol to less than or equal to. And indeed, that is the domain of the reflected function given by y equals square root of minus x. The function is defined for x equal to 0 or x negative. So at -4, for example, you take the opposite of -4 to get 4, and then you take the square root to get 2. So actually, you can define this function for negative values of x because there's a minus sign in front of the x. So the domain is what we would expect based on the fact that minus x should be non-negative. That means x should be non-positive. Now looking at example 5, draw a rough sketch of the given function. Again, we won't look at these point by point. We'll just try to get a general idea of what the graph looks like. And this would be useful, say, if you're using MyMathLab and you're identifying a graph based on like a multiple choice type question where there are several to choose from. Y equals minus x cubed. Now, our parent function here is the cubing function, f of x equals x cubed. And our transformation here could be described as f of minus x, the minus sign being applied to x. This would correspond to a reflection about the y-axis. Now the cubing function, just to give you a general idea, rather steep curve that sort of flattens out a bit as it goes through the origin, and then it continues increasing on its way. If we reflect this across the y-axis, what we're going to see is something that looks like this, a decreasing function. Same shape, but now it's decreasing rather than increasing. Now there's something else to note about this example. It's rather interesting actually, that the way the graph appears when you do a y-axis reflection is identical to how it would appear if you did an x-axis reflection, which would suggest that for this particular function, a y-axis reflection is equivalent to an x-axis reflection. Now the reason that that's the case is because we're dealing with an odd exponent. If we consider what happens when we cube minus x, we should see it's really equivalent to minus x cubed. In other words, it's minus f of x. So y equals f of minus x in this case is the same as y equals minus f of x. F of minus x equals minus f of x for all x. That is, f is an odd function. When you have an odd function, you can't distinguish a y-axis reflection from an x-axis reflection. F of minus x is a y-axis reflection. Minus f of x is an x-axis reflection. If the function is odd, the two types of reflections should yield the same graph. And that's exactly what we're seeing in this example. So we can tie this in with what we talked about in regards to even and odd functions. Second example, y equals minus x squared plus 2. Here the parent function is f of x equals x squared. And the transformation could be expressed as y equals minus f of x plus 2. Now here, the minus sign is being applied to f of x, which means we're dealing with an x-axis reflection. In addition, with the plus 2 added on to that, we're going to have a shift up 2 units. Now, a question that is important here is which transformation should we apply first? The reflection or the upward shift? The answer here is we should do the reflection first, because actually the reflection indicates a multiplication by -1. It's -1 times f of x plus 2. And by the order of operations, multiplication has priority over addition. So first of all, we should apply a reflection across the x-axis to f of x equals x squared, and then take that and shift it up 2 units. So we're dealing with a parabola, vertex at the origin. If we reflect it across the x-axis, it would be upside down, like this. And then if we shift every point up 2 units, then the vertex would now be at 0, 2. The shape should be the same. Just now we have every point shifted up 2 units. Again, we're just trying to get a rough idea here. It's not perfect by any means, but it's close enough to give us a pretty good idea of what the graph would look like. This is one of the advantages of knowing transformation rules. You can look at an equation like y equals minus x squared plus 2 or something along those lines and visualize what the graph is going to look like before you plot a single point. And that is a big advantage when it comes to graphing functions, knowing what the graph looks like before you even set your pencil to the paper. It's very useful. So being able to produce these rough sketches, they're rough sketches, but they're actually fairly accurate. It's very useful for getting a quick idea of what the graph of a function looks like. We now turn to a couple of what are called non-rigid transformations, meaning that although the basic characteristics of the graph will be the same, the shape, the actual shape of the graph will change. And here we'll look at vertical stretches and shrinks of a graph. Given a function f, the graph of y equals a times f of x is the graph of f stretched vertically away from the x-axis if a is greater than 1, shrunk vertically towards the x-axis if a is less than 1 but greater than 0. So what's happening here is a multiplication of the function by a positive constant a. And that has the effect of stretching the graph away from the x-axis or shrinking it towards the x-axis. There's also a horizontal stretch or shrink where rather than multiplying f of x, we multiply x by a. However, you will not be held responsible for that particular type of non-rigid transformation. So we'll just focus on the vertical stretch or shrink factor. But just keep in mind that that is related to multiplying the function by some constant a. So on the next video, we'll look at, start with example 6 and look at a couple of examples of this type of transformation.